Our first speech is the keynote speech from Professor Xia from China, and we're super excited to have the professor with us and to hear his keynote speech. Professor, I would like to invite you to,
First of all, many thanks for Igor's invitation. So it's my great honor to present some of our recent studies relevant to large language models for software engineering. So this slide summarizes the key question I would like to answer in my talk today. Is state-of-the-art LLM a silver bullet to automated software engineering? So I'm Xinxia, so I'm currently working at Huawei Technologies. So as we all know that large language model is changing software engineering. So it achieves significant progress in generated code examples. And since its first appearance in the year of 2019, that is Google's T5. So now if you check the news, you can find every month there would be a new kind or several new kinds of large language models. And large language models change the software engineering actually at the end of the year of 2022. So at that time, actually, we find ChatGPT can performs very well in various software engineering tasks like code generation, code recommendation, and also development question and answering. So there's many tools based on the large language models. For example, Copilot X or Copilot is one of the most famous tools, which incorporates many LLM-based functionalities, and it has many amazing performance. For example, in code explanation. So the main idea is to give you a piece of code. We use LLM to generate the natural language description of the code to tell developers the intention of code and also the behavior of the code. And another example is the code translation. It's more like when you write the code in Java, so it can be automated translated to C# so that you don't need to develop different applications for different platforms. And another application is the brushes. So this is more like the software quality insurance tool. It provides like code formatting, bug fixing, debugging, and the comment generation functionalities to help improve the code quality. And some other example is test case generation. So give you a piece of focal method, that is the method you need to test. So due to the amazing performance of large language models for software engineering, so we would like to explore what is the limitation of large language models. So whether it is a real silver bullet to solve various problems. So that is why we performed this study last year. So we selected 4 tasks from software engineering, covering from software development, maintenance, testing, and quality assurance to explore their limitations. For the software development, we choose the code generation task. So the main idea is to give you a piece of natural language description. We ask the ChatGPT to generate the code to solve the problem. So we use the human evil dataset by evaluating using a PassAT-K scores. The second task is the code documentation generation. So we give a large model a piece of code. We ask it to generate the natural language descriptions. So we use the code search net dataset to evaluate the performance. And in the testing, we choose the test case generation. So we give ChatGPT a piece of a focal method. So we ask it to generate unit test cases. So we use the Diffbot4j dataset and evaluate using the coverage, like line coverage and branch coverage. And the last task we choose is automated program repair. So we give ChatGPT a piece of code containing bugs. So we ask the model whether they can generate the patch with the bugs fixed. So we use the quick bugs dataset as example. So this is 4 tasks we explore. And also we use various large language models like the GPT 3.5 Turbo, that is ChatGPT, and another 2 models. and we try to analyze different research questions like the performance of these large language models in software engineering tasks and the influence of few-shot learning on the performance. Because we find that sometimes you give more examples to larger model, the performance can be very different. And also the robustness of different prompts. We also find that the prompts, the design of prompts can affect the performance. So we use actually three kinds of prompts. The first prompt is following the tutorial prompt engineering tutorial by fulfilled and end. And the second is a simplified prompt. We simply omit the details of the tasks. And also the third kind of prompt is from the OpenAI recommendations. So this you can think more like the more moderate level of specific task information. So these are the results of our study. So first of all, in terms of code generation, we find that ChatGPT or GPT 3.5 tuber performs the best compared to all of the baselines, like some BERT models and other models. So for example, in PassET1 in the Python programming language, it almost achieves 70% of improvements. And one interesting thing is in the field short learning, we find in Python, the zero short learning performs the best. This may be due to when you train the ChatGPT models, it has already incorporated many Python code, so it can understand the Python very well. But for C++, we find that field short learning performs better. And for the different prompts, still we find that a default prompt, which follows the prompt engineering tutorial, performs the best compared to other prompts. And also for the test case generation, code document generation, and program repair, so the result is different. For example, in the test case generation, we find that ChatGPT performs the best. And when you have more examples to the large language model, it can perform better. This is due to that large language model did not say too much test case generation tasks. So if you can give it some examples, it can shows improvements. And also we find that still the default prompt shows the best performance, but there is no statistically significant difference. But for the code document generation, we find that ChatGPT does not perform well as the distill code T5 model. This is due to for these traditional models, has already used a lot of fine-tuning or the retraining process, which contains a lot of code and its comment pair. But for ChatGPT, it does not say too much information. So that is why when you use few short learning, the performance is improved. And also we find the default prompt shows the best performance. And for the program repair, I think the result is similar as the code generation. The ChatGPT performs the best, and also zero short learning already performs the best, and also the default prompt performs the best. So based on the results, actually, we found that large model is overall very promising to solve software engineering problems, but still we find it has many limitations. So I will use two of our recent studies to show what these limitations are. One is about the output actually is inconsistency. So sometimes it will give you the contradictory results. And the second thing is about the robustness of the prompts. We can find even you change the prompts a bit, the results can be totally different. So the first is one thing we find as shown in the SW bench, the paper. Actually, they find when you ask ChatGPT or large language model to solve real GitHub issues, it can only solve the real problem with less than 4% of the problem. But now I think there are many papers try to works on based on the SW bench, and they can show that this performance is increased to 30%. So the main idea is when you give ChatGPT or large language model are real software issues, it's harder for it to generate the patch. So this is the golden patch. This is the patch generated by large language model. So this is one limitation. It cannot assist in fixing actual bugs. So actually, the first limitation is the LM produce the self-contradictory results. So this is example. So when you give ChatGPT or a large language model requirement, you want it to write the correct code and it generates the code. But you ask it again because this code is wrong. It can tell you this code is correct. Actually, this code is wrong. So based on this one, we perform an experiment. Actually, we find, for example, sometimes when it said it produces the buggy code, but you ask it again, it can tell you the code is correct. This is example. So when it generates the incorrect code, but you ask it ask it to do the self verification, they tell it the result is correct. Another example is we named as uh, hallucination. So you generate the incorrect code, but you ask the large language model again. So it says, so no, this is correct code. This code is wrong. It also gives you the solutions to fix the bugs here. So based on this one, we find there are lots of limitations. This is one part. Another part is relevant to the robustness of large language model for software engineering. So this is an example. So when you give the prompt as like showing this slide, it can generate the correct code. But you add one more it here, so it can generate the wrong code. But now the problem is in the past works, they always do the random perturbations. This will cause the problem. So based on our study, we correct the real perturbations from developers, and we conclude 21 categories for perturbations. It's like, for example, like split the function into two and add two more twos. This is like the example. So the main result is we found that the frequency of the perturbations increase. The number of the code will fail on more generate on more tests. So for example, if there's only one kind of perturbations, it can pass no perturbation, it can pass all the tests. But when you add three types, only five you can pass only 10 out of 15 test cases. So this is the limitations. So based on the limitations and amazing performance, so we can show that when we are designing software engineering tasks, so we need to consider these limitations, and we should not use large model just as a input and output tool. So we need to consider domain knowledge. So I used three examples. So the first example is about the code generation. So due to time limitation, I will not go in detail. So the main idea is when you want to generate the code, you search from the code space to find the most relevant code, and you get the most relevant code. Then you ask the large model to perform the code generation based on your code context. And in this case, you can improve the performance a lot. So this is the main idea of the study. So actually, we find that by using the simple way to use the retrieval augment approach, so it can when incorporate with simple models like CodeGPT or ChatGPT, the performance can be improved a lot. So this is one lesson we learned. We need to consider the similar code to improve code generation. And the second is relevant to identify the silent vulnerability fix. So the main background is before you disclose the vulnerability public, so there would be sometimes it is a silent fix. The attackers can detect this kind of vulnerability fix patch and attack the system. So we want to detect whether a patch really fixed a bug before it is disclosed publicly. So the main idea is still we use the BERT model. So we learn from the positive and the negative vulnerability fixes and build a model to perform to solve three tasks. One is to detect whether a patch is vulnerable or not, and it's the exploratory rate, whether it's a serious vulnerability, and it's the CWE category to identify the categories. So the result is also very good. So I will not go in detail. So last test case is about test case generation. So actually the main idea is we use ChatGPT to generate the chain of sort data set. And this is example. So we give like ChatGPT a focal method. So we ask it to generate the test intention and the possible test input. And then we use the COT data to fine tune our code llama model to based on the coverage reward feedback to improve the model to achieve the best coverage for the trained data set. And then we use the trained model to generate the test cases. So this is the main idea. First is about the generation of the COT data set, and the second is use the coverage reward model to regenerate and improve the overall coverage of the system. So the results also shows that our approach shows the best performance. And this is from GPT 3.5. Although GPT 3.5 sometimes shows better performance, but overall our approach shows is better. And this is some test cases we generate. For example, this is the focal method. This is the test case generated by Stackholder, and this is test case generated by our model. You can simplify it, consider the possible inputs and also Oracle problem. So this is a summary of my talk. So first of all, I showed that LLM shows promising performance in multiple software engineering problems, but there are still many limitations in LLM for SE and which we should solve in the future. And also I use 3 example researches to show how to incorporate LLM to solve various software engineering tasks. So this is my main talk today. Thank you.
Thank you very much.